So today we are going over the IVT, MVT, and EVT theorems in calculus. Let's begin with the IVT or intermediate value theorem. Typically, you'll be given 2 points on the x-axis and their corresponding y value, more commonly written in function notation like f of c equals d. IVT only applies to continuous functions over the given interval and allows you to conclude that for any y value between these points, the function must cross it at least once between the x values of these points. This is true for any kind of continuous graph you can think of. It doesn't even have to be differentiable, because with the continuous function, you can't get from this point to this one without crossing all the y values in between. More formally, IVT is described as there's at least one x value k between 2 points of a continuous function so that f of k equals the given y value in. Next up is MVT, or mean value theorem. Again, we are given 2 points on a graph. We have to use the average rate of change, or the slope formula, to evaluate the slope of a line connecting these points. The top of the formula gives the change in y values, and the denominator gives the change in x values. Dividing these gives rise over run, or the slope. MVT states that between the x values of these points, there's at least one point that has the same slope as the line connecting these points. This only applies if the function is continuous on the open interval c to a and differentiable on the closed interval c to a. This works for any type of graph that satisfies those conditions and can be true at multiple points, as MVT guarantees at least one x value k, where the slope at that point is equal to the average rate of change of that interval. Lastly, there is EVT, or extreme value theorem, which concerns a graph's extrema. EVT states that on a closed interval, a function must have an absolute minimum and maximum if it's continuous. Now, we can apply EVT to find these extrema. In this example, I'll find the absolute maximum point on this graph. Notice that over a closed interval, an absolute maximum could only occur at the peaks or endpoints of the graph. Looking at it this way, we can consider the absolute maximum point to be the peak or endpoint of the interval that has the highest y value. Setting the function's derivative to 0 allows us to solve for all the x values with the horizontal tangent line, or the peaks of the function. We can make a table of candidates with these x values to compare their y values. In this table, also include the endpoints of an interval, because an absolute maximum could occur there. Plugging these points into the original function gives us the y values. Since the absolute maximum has the largest y value, a quick comparison would reveal that there is an absolute maximum at x equals g over the closed interval a to g.